Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. We know that Fourier theory is extremely useful because we use the S1 symmetry to decompose the space of square integrable periodic functions into S1 irreducible modules. And this naturally begs the question, what about irreducible modules over other Lie groups? So that's what I want to look at in this video. I want to look at irreducibles over the next interesting group, which is SU2. The group of special unitary 2x2 matrices, and we'll do that by using the Lie algebra Lie group dictionary. So instead of looking at the Lie group, we'll look instead at the complexified Lie algebra SL2C. Okay, so remember, in fact, we can in fact move from the Lie algebra to the universal enveloping algebra. So that's what I'm going to do. I'm going to let U be the universal enveloping algebra of the complexified Lie algebra SL2C. And just to remind you what this Lie algebra is, firstly, as a vector space, it's just this space of 2x2 complex matrices with zero trace. Okay, so that's what happens when you differentiate the condition that the determinant is 1, you get trace is 0. And then the Lie bracket on this is just the commutator. Okay, so the commutator of A and B, remember, is AB minus BA. Okay, so the first thing I want to mention is that if you want to study modules over this, and the finite dimensional ones over this here will correspond to finite dimensional SU2 modules, then we can in fact reduce ourselves to the case of irreducible modules. So what's an irreducible U module, V? An irreducible one is precisely one whose only submodules are 0 and V. And what's the reason that we can actually reduce our study to just the irreducible ones? Okay, and that's a property known as semi-stability. So let me just state the theorem which gives you semi-stability. Okay, if you have any finite dimensional module over this universal enveloping algebra U, then it is actually a direct sum or isomorphic to a direct sum of irreducible ones. Okay, and since the direct sum procedure is quite a simple procedure, that means to understand any such module, really you just need to understand the irreducible modules. Okay, so if you've seen the theory of representations of finite groups, this will be familiar to you because you know that over the complex numbers, if you look at any complex linear representation of a finite group, then it is a direct sum of irreducible modules. And actually the same type of proof works this way here as well if you work with the compact group SU2. So you don't have something which is finite anymore, this group, okay, but it is compact, and compact is good enough because in this case you actually have something called a Haar measure. You can integrate, and so you can take the average over the group SU2 because of this Haar measure. So normally when you want to try to prove this theorem in the case of modules of a finite group, okay, then you use the averaging trick, okay, and here the averaging trick works as well because you can average over SU2. Okay, so that's all I want to say about the proof of that theorem. And what it does, remember, is it allows us to reduce to the case of irreducible modules. So we're going to try to study irreducible finite dimensional U modules. Okay, so let's have a deeper look at this universal enveloping algebra. What does this universal enveloping algebra look like? So firstly, it has three generators, E, H, and F. And the easiest way to think about what it is it's generated by these three differential operators. E is x d dy, H is x d dx minus y d dy, and F is y d dx. Okay, so they're the generators, and we need to know the relations as well. And of course, the relations we know, so these are actually in the Lie algebra. They correspond to elements of the Lie algebra. And as usual, the relations are the Lie bracket. So for example, HE minus EH is going to be, and you take the, or rather the commutator inside the universal enveloping algebra is the Lie bracket. And the Lie bracket of H and E turns out to be 2E. Okay, and we can get the other two relations as well. So HF minus FH equals minus 2F. And EF minus FE is equal to H. So they're the three relations that gives you everything. Okay, so why is it true? So I won't do the whole calculation here. It's quite a long calculation, but it's fairly easy, and you'll see enough so that you can get a feel for what's going on. So firstly, remember, what is SL2C? This Lie algebra here, okay, they're the traceless matrices, okay, so all of 2 by 2 matrices, that's 4-dimensional. When you insert the trace equals 0 condition, you'll get 3 dimensions left, so we can span it with these 3 matrices here, which are clearly traceless. 0, 1, 0, 0, 1, 0, 0, minus 1, and 0, 0, 1, 0. Okay, so if you looked at my previous video in this playlist, you would see that you can exhibit this universal enveloping algebra as differential operators not on the Lie group, but also on the xy plane as well. Okay, and if you do that, what does this matrix here correspond to? Which differential operator? So since it's in the first row, second column, it's x d dy. What about this one here? So there's a first row, first column, so that's x d dx, and there's a minus one here, that's minus y d dy. And thirdly, there's the this matrix here, which corresponds to, it's in the second row, so that's a y d dx, y d dx. Okay, so they're the generators. In the universal enveloping algebra, we know where all the relations come from. Okay, so where do all the relations come from? Just the commutator of the generators like this come from the Lie bracket. So they're the 3 possible commutators that you have, okay, that give you non-trivial relations, and you just need to compute. And you can compute either just by doing the matrix product and working out the commutator, but I'll do it in terms of the differential operator because I want to emphasize that this is a very natural way to think about this universal enveloping algebra. Okay, so here you have HE minus EH. Let's check that it does equal 2E, okay, and the other two will come, computations will follow similarly, okay. So what's HE? H was this x d dx minus y d dy, and we're going to compose it with this E, which is x d dy, okay. And then you have to subtract the EH. The E was this x d dy, so there's the x d dy here and here, and that's multiplied by this H, which is x d dx minus y d dy. And what we're going to do is we're going to look at the middle terms. So there are 4 things here, right? There's linear functions and there's derivatives, partial derivatives. Okay, so we're going to look at the middle two, like d dx and x. Now, in this case here, we have a Wahl type relation between them. These do not commute. Okay, remember this is a non-commutative algebra. So the Wahl relation is that this is equal to x d dx plus 1. Okay, and that's quite easy to see. Here you have d dy and x, they commute. Here you have d dy and x, they commute, okay, because x is constant with respect to y, so you can pull it out. And finally, here you have d dy y, so you have to use the Wahl type relation to commute these to get your y d dy plus 1. Okay, so let's commute this through, okay, using this formula here. You'll get something which is the first term, x times this first term is x squared d dx times d dy, x squared d dx d dy. Well, that will cancel with this x squared d dy d dx, okay, because the x pulls out there. So they cancel, and it's just the second term that you have left, okay? So you have 1 in the middle here, so you have x times d dy. We'll write that in, okay? So we get there 1 copy of x times d dy, okay? Here what you have, these commute, so you get yx times d dy d dy, or d2 d dy squared. Okay, what about on this side? You've also got 1 extra term, where you've got a d2 dy squared, and that's xy times d2 dy squared. That's from the first term here, so they cancel, and what you have left is this second term where these two become a 1, so you get x d dy. There's an x d dy, so that's a minus x d dy, so you get 2 of them, and this x d dy was just e. So we see very easily from this computation too that we get the desired relation here. And a similar calculation, either using differential operators or just computing commutators of matrices, gives you the other 2 relations as well. Okay, so we're going to use these, and it's quite interesting what these are, okay, these relations are. And the key to this, and this is kind of the combinatorial analysis for SL2C modules, okay, and that involves the analysis of weight spaces. Okay, so remember, if you have look at modules just over essentially with the action of a single element, okay, so essentially modules of the polynomial in that element there, you're just looking at eigenspace theory. So what we're going to do is we're going to look at this nice element here, H, which corresponds to this diagonal matrix, and we're going to first look at the eigenspaces of that. Okay, so if you want to get a submodule, it has to be of any module. Okay, it has to be invariant under E, H, and F, and in particular invariant under H. So you might as well look at some eigenspaces. Okay, so we'll fix V here, finite dimensional U module, and we'll look at the eigenspaces of H. So Vn will be the eigenspace with eigenvalue n. And because this is typically the element that you choose, this diagonal element here in Lie theory, we call this a weight space, and the weight is n. Okay, so that just means a special type of eigenspace correspond to a special element of your Lie, in this case your Lie algebra or universal enveloping algebra. Okay, so what's very nice about this? So firstly, E and F behave very nicely with respect to these eigenspaces. Now, normally if you have E and F commute with this H, then what it does is it preserves the eigenspaces, but they don't. But nevertheless, there is some interesting relationship between them. If you let E act on the weight space with weight n, it gets contained inside the weight space with weight n plus 2. Okay, what does F do? F shifts these weight spaces back instead. It sends Vn into Vn minus 2. Okay, so if you remember the quantum harmonic oscillator, you'll see a similar sort of phenomenon happening there. Okay, so and it's the same type of calculation which I want to show you now. Okay, so both of these they have a similar proof. The proof of part A uses this relation here, A here. The proof of B just uses the analogous relation over here, and the fact that the difference between these two is here the commutator gives you plus 2e, here the commutator gives you minus 2f, and that's why there's a difference in whether you shift up or shift down. Okay, so let V be inside this weight space Vn here. Okay, we're going to apply E to it, so EV. We need to check that it's inside this Vn plus 2, so we're going to check that it's an eigenvector with eigenvalue n plus 2 for H. Okay, so we let H hit it. So this is HE acting on V. And the key is that now we can rewrite this EH using this relation here. Okay, EH is just, or rather HE is just EH plus 2E. HE is just EH plus 2E. So let's break up into two parts, EH times V and 2EV. And we use the fact that here V is an eigenvector for H with eigenvalue n. It's inside Vn. So this means it just gets scaled, H just scales V by n. So that's just NV. So that means that we can pull this scale out n to get you n times EV, and you've got another 2EV here. So in total, you've got n plus 2EV. Okay. So when you take this EV, you hit it by H, okay, all you get is a multiple of that original EV, and that multiple is n plus 2. So EV is an eigenvector, and its eigenvalue is n plus 2. So you do indeed land in here, so part A follows. And the similar proof holds with F, part B. When you use F, the only difference is that the commutator here gives you the minus 2F. Okay. So that's rather nice, okay, that E and F respect these eigenspaces in this way, okay? So they don't preserve the eigenspaces, but they move them in a very specific sort of a way, okay? So that's going to give us a very important corollary and also a definition that we shall use, okay? So there's an eigenvector V for H. Well, there are always lots of eigenvectors, okay? From eigenvector theory, we know this because V is finite dimensional, but we can find one that further is such that E times V is equal to 0. Okay, and we call such an eigenvector a highest weight vector. Okay, so why is it called a highest weight vector? Remember, the weights are just the eigenvalues. Okay, so suppose you start with any eigenvector W, right? Start with any eigenvector W, say here. If you apply E to it, you're going to land in this eigenspace where the eigenvalue is 2 bigger. So potentially that gives you a bigger, a eigenvector with a bigger eigenvalue, a bigger weight, okay, unless it's 0, okay. So that's an easy way to make eigenvectors with bigger eigenvalue, and the only obstacle is when it's 0. So when it's 0, okay, that means that you can't use this method of hitting by E to get you a eigenvector with a bigger eigenvalue. So that's why it's called the highest weight vector, because by applying E to it, you can't get a bigger eigenvector with a bigger eigenvalue because it's gone to 0. Okay, if it weren't 0, then it will have an eigenvalue which is 2 bigger. Okay, so let's prove this. Okay, and it's quite easy to prove actually. Okay, and it gives us a powerful way to understand irreducible U modules. Okay, so we're going to start with any eigenvector W, and we just keep hitting it with E. So we get EW, E squared W, EQ and so forth. And what do we know? We know that by this proposition they're learned in different eigenspaces. Okay, so if they're in different eigenspaces, if they're all non-zero, then they must be linearly independent. Okay, but that's an infinite list, right? And this module here, V, is finite dimensional. So eventually it must be linearly dependent. So the only way that can happen is at some point you get a 0. Okay, so you keep applying this and you eventually get 0. So the last non-zero one is such that when you apply E to it, you'll get 0. And it is an eigenvector because of this proposition. Okay, these are all eigenvectors for H. Okay, and it is the highest weight vector. And that gives you this result here. Okay, so now we come to our main theorem, which classifies all the irreducible SL2C modules. Okay, so suppose we have an irreducible U module V, and the dimension of this is finite. We look at the finite dimension ones only here, and the finite dimension is D plus 1. Then this module V is actually just this module here, CXYD, and that just means the homogeneous degree D polynomials in X and Y. So in other words, just the span of the monomials x to the d minus 1y, all the way down to y to the d. So clearly this has dimension d plus 1, and also, as you've seen in my previous video in this playlist, this is actually a module over U, okay? And that's quite easy to see too. Okay, so before I give you the proof of this wonderful theorem here, I want to make some important remarks. So the first thing is that these are, well, we've seen that they are actually modules over U. They are all irreducible. So that's the first thing, okay? So this gives you precisely all of them, okay? This is irreducible, and that's fairly easy to see from the proof that we'll give you there, okay? So the second thing is that, of course, well, one of the things that we've been looking at are weight spaces, okay? And I claim that this is actually the weight space decomposition of this module V here, okay? So what are the weight spaces? They're basically the eigenvectors, or eigenspaces rather, of this H, and H was x d dx minus y d dy, okay? So what does x d dx minus y d dy do to all of these monomials here? So for example, in this first one, y d dy sends that to 0, x d dx, so firstly d dx, you get d times x to the d minus 1, and then you increase the degree of x by 1, so you'll get d times this x to the d. So the first eigenvalue is d here, okay? When you move to the next one, okay, here you get from x d dx, you basically get d minus 1 copies of this, but from the minus y d dy, you get minus 1 copies of this, so you get d minus 2 is the next eigen value here, and so forth all the way down to the last one, which is minus d. So this is going to be give us the highest weight vector, and that weight is going to be d here, okay? So I guess if you want to show that this is irreducible, it's quite easy. What you do is you firstly realize that to have any submodule of this, non-zero submodule, you need to have a direct sum of eigenspaces of H. So there have to be a direct sum of these. And the point is that if you're going to apply x and y, e and f rather to these, what you will end up doing is essentially moving these weight spaces over, and you'll eventually actually generate the whole of this, okay? So that's why this is irreducible. The other thing is that this, of course, gives you all the finite dimensional irreducible modules over SU2. But what about SO3? So remember, SO3 is a quotient of SU2. It has the same Lie algebra as SL2C, okay, when complexified. So this also gives you the SO3 modules, but you have to be a bit careful here because the SO3 modules are the SU2 modules for which minus 1 acts trivially. Okay, so remember this is essentially isomorphic to SU2 modulo plus or minus 1, that normal subgroup plus or minus 1. And so if minus 1, how does minus 1 act? Well, minus 1 acts, remember, by sending x and y just to their negatives. So if you want that to act trivially, since the total degree here is d, you want d to be even, so that because the action of minus 1 will be just minus 1 to the power of d. So the SO3 modules amongst here are precisely those where d is even. And since the dimension is d plus 1, they're the odd dimensional ones. Okay, so the odd dimensional irreducibles of SU2 are precisely irreducible SO3 modules, okay, finite dimensional ones. Okay, so there are the remarks, and I want to give you a proof of this theorem, which is very nice, okay? So we're going to start, remember, there always exists a highest weight vector. So we're going to pick highest weight vector v, and I need to exhibit this isomorphism. So I claim that the isomorphism comes as follows, okay? So we're going to pick essentially these monomials, but we'll scale them, okay? So we'll pick these monomials, okay, but we'll scale them by this factor d factorial d minus I factorial, and we'll call that pixy, okay? So that's essentially the monomials, but with some scaling factor. And I claim that if you map this over to fi to the v, okay, so this is the basis for this U module here, okay, so there is a linear map, a unique linear map which extends this. I claim that that's an isomorphism, not just of vector spaces, but actually of U modules, okay? And to do that, I need the following little lemma, which is essentially a calculation. Okay, so what I'm going to do is I'm going to look and see how h and e act on these vectors here, fi to the v. So firstly, h of f to the iv is just a scalar multiple of f to the iv. It's n minus 2i times f to the iv. What about if I let e act on f to the I plus 1v? Well, what it does is it sort of maps you back from fi plus 1v to f to the iv up to scalar. And this scalar tau subscript n comma I is going to be what? This tau ni is basically the sum of this arithmetic progression, n plus n minus 2 plus all the way down to n minus 2i. So that's what that is. It's a sum of an arithmetic progression. So if you want, you can sum this. There are I plus 1 terms, so it's I plus 1 times the average of the first and the last term. The average of the first and the last terms is just n minus I. Okay. So let's see why this is true. Part A is actually very easy. And the reason why, remember, is that V is an eigenvector for H with, we said, eigenvalue. The weight is n here. Okay, let's suppose that the weight of this highest weight vector is n. And each time you hit this eigenvector with F, you get another eigenvector, but the eigenvalue reduces by 2. So if you hit it I times with this F, the eigenvalue has gone down to n minus 2i. So that gives you part A. What about part B? Part B requires a little bit more of a calculation. Okay, so let's look at the left-hand side. I'll write this left-hand side as E times F to the IV. And we're going to use induction. Okay, so you can check the base case. It's not too difficult what happens there, but let's look at the inductive step. And here you want to use the relation EF, so we haven't used the third relation yet, remember? So the commutator of E and F is H. EF is equal to FE plus H. Okay, so let's expand this out. FE times F to the IV and H times F to the IV. Okay, so we need to study those two quantities here. So the first thing is that this part here you can analyze by induction. So we're going to assume this is true for smaller values of I. So when you reduce I to I minus 1, you'll get this e to the FIV. And the right-hand side, you have to reduce I, so you'll get tau n I minus 1. And then you'll have f to the I minus 1 v. Okay, so that's what you have there. Let's write it a bit neater. So that you have that there. So tau n I minus 1 f to the I minus 1 v. And this second part here, you can use part A. This is an eigenvector with eigenvalue n minus 2i. So you have an f to the I minus 1 here, but this is a scalar you can pull out, so you just get f to the IV. So at the end of the day, you'll just get some multiple of f to the IV. And what's that multiple? So you've got this tau n I minus 1. So that's the sum of all these terms up to everything but the last one. And then you add the last one. So you'll get tau n I here. And that gives you precisely this relation here by induction. And I'll let you check the base case. So this lemma finally is proved. Okay? And that's going to be the key. It's going to allow us to prove this main theorem here. Okay. So let's look at the first corollary of this lemma. Okay, the first one is that this v is actually spanned by all these powers of f, and the powers of f, or rather powers of f applied to v. So v up to f to the dv. So that's the first fact, which is wonderful, and it means that that this indeed gives you at least an isomorphism of vector spaces. Okay, because these will give you a basis as I runs from 0 up to d. Okay, so let's see why that's true. So the first thing is that we're just going to look at the span of v, f squared v, and so forth. Okay, you look at just all of this, okay, and see what happens. Okay, what the lemma tells you is that this is actually a U submodule of the irreducible module v. Okay, because I claim that this is actually closed under the action of E, F, and H. So certainly if you apply f to any element in here, it stays inside here. If you apply h to any element inside there, okay, it just scalar multiplies it. And if you apply e to any element inside there, what you'll get is you'll get the previous element up to a scalar. So this shows you that the linear span of all of these is closed under the action of E, F, H, and hence under multiplication, scalar multiplication by elements in U. Okay, so that means that you get a U submodule, but V is irreducible, and you've got this non-zero element, this highest weight vector, which is an eigenvector in here. So in fact, it has to be the whole of V. Okay, so basically V is just the cyclic module generated by this highest weight vector V, and in fact you can say how it generates. It's given by just these powers of F times this V. Okay. So of course, these are all lie in distinct weight spaces, so they're going to be linearly independent until eventually it gets 0. We've seen this argument before. Okay, so that means that eventually it will go to 0, but we know that the dimension of v is d plus 1. So the time when it goes to 0 is precisely f to the d plus 1 v, and this is the last non-zero one. Okay, that's what it has to be, because they're linearly independent, and so and what you'll get is the whole of v, and that gives you that corollary. Okay, so now we've got a good grip on what this v is. Okay, it's going to be, as a vector space, it's going to be like that, and we've got some knowledge about its how this acts. Okay, the h and the e and the f act on this. So the second corollary of this lemma, which is very important, is the identification of what that highest weight is. This highest weight is not independent of this d. Okay, in fact, it equals d. And the way we'll get that, that's rather neat, is we're just going to use this expression here, which holds all the time. Okay, in particular, it will hold also for I equals d. Okay, because we've proved it by induction. Okay, so let's look at it when you have I equals d. Okay, so you're looking e f to the d plus 1 v. Now f to the d plus 1, that's going to be when it's 0. So this is actually equal to 0. Okay, so this side here will be equal to 0. On the right-hand side, you'll get tau n d f to the dv. Tau n d f to the dv. Now this f to the dv is the last basis element over here. That's non-zero, so that means the scalar out the front has to be 0. That's tau n d equals 0. Here's your tau n d. Okay, when I equals d, and this has to be 0. Now this is an arithmetic progression. Okay, you start with n, and then you add n minus 2, then add n minus 4, and so forth down to this one here. Okay, so it will turn out that if you're adding just negative numbers, of course, you'll never get there. But so let's suppose that n is going to be positive now. You keep adding smaller and smaller positive numbers, and then you start adding negative numbers, and eventually you'll get smaller and smaller until you come back to 0. So what's the time when you come back to 0? We start with n, you go to n minus 2. Of course, the time you get back to 0 is when this is symmetric, and you end up here at n minus 2n, okay, which is equal to, so this is n minus, so that must be minus n, okay? So that's the time, okay, when it's equal to 0. okay? But that has to be tau in D. The I has to be equal to D there, okay? So this has to equal n, I has to equal n for this sum to be 0, okay? You know when I equals n, this sum is 0. If I is any smaller, it'll be bigger than 0. If I is any bigger, then you'll get less than 0. And well, the case when that happens is when n equals D. So that identifies the highest weight with this D, which is 1 less than the dimension of your irreducible module. Okay, that's fantastic. Now the final thing that's required is just to compute, to check that this is an isomorphism, okay, not just of vector spaces, which follows from the corollary 1, but actually of U modules. So basically you want to say that E, H, and F act on this side the same as on this side. Now the key to how H acts is from this here. It acts as n minus 2i, f to the iv, okay? And so the point here is that's where we use corollary 2, okay? N equals D, so it's just D minus 2i. That's how it acts. And remember, these are up to scalar. They're just the monomials, and we saw that what are those eigenvalues? They're just D minus 2 down to minus D, okay? So you can check that H acts on these the same way that it acts on these. So let's do something slightly different. Let's see how E acts on them. That's a little bit more interesting, okay? The way that F acts is also quite easy to see, okay? So we'll do the more complicated one, and we'll see how does E act, okay? So we're going to look at how does E act on the left-hand side, Pi plus 1 xy. Pi plus 1 xy. So this I plus 1 xy, so we're going to look at a scalar multiple of x to the D minus, and the I was I plus 1, so it's minus I minus 1 times y to the I plus 1. And the scaling factor out here is D factorial on D minus the I plus 1, so it's D minus I minus 1 factorial. And E is x d dy. So we're going to do this derivative like that, okay? So what happens? So the d dy, okay, so the first thing is that you differentiate with respect to y, so you've got an I plus 1 coming out the front. Okay? The other thing is it reduces the degree of y by 1, and you multiply by x after, so you increase the degree of I by 1. So basically one of the y's gets changed to an x, so you get x to the d minus I. X to the d minus I, y to the I. And you want to write this in terms of pi instead of, so you want to write with the coefficient of d factorial and d minus I factorial. Okay, so you have an extra thing in the denominator compared to the d minus I minus 1 factorial. You've got an extra d minus I. Okay, and what is this term over here? Remember, n equals d. N equals d. So this is just tau di. Okay, n equals d here. And this term here, d minus I times I plus 1, d minus I times I plus 1 is just tau di. So what you get is no longer pi plus 1, you get pi, and the scalar out the front is 2 tau di. And that's exactly how E acts on f to the I plus 1v, which is the corresponding element over here. Okay, it just multiplies by, remember, n equals d, tau di of FIV. And so that essentially completes the proof that this irreducible module V is isomorphic to this one here. So this gives a complete classification of all the irreducible modules over SL2C, the Lie algebra, and hence all the finite dimensional irreducible SU2 modules, and also the finite dimensional irreducible SO3 modules. I hope you enjoyed this adventure in pure mathematics.